Hi everyone. So in this video, we are going to discuss the topic of motional EMF. Okay. So first, let us understand the meaning of this term, motional EMF. Like if you have a conductor, okay, conductor in the shape of a rod or in that matter of any shape. Okay. Now, if this conductor is moving with some velocity in a region of magnetic field B, then an EMF is developed across the two ends. Okay, so these two ends of the conductor, an EMF is induced, and this EMF is called motional EMF. Okay, so basically it is an EMF induced in a moving conductor. Okay, EMF induced in a moving conductor in magnetic field so it is called motional EMF. Okay, so basically in this video we are going to derive the expression for motional EMF. We will also analyze the direction, how to find the direction of EMF. Okay, so these two things we are going to see in this video. Okay, so let's start. Now suppose we have a U-shaped wire. Okay, this is a U-shaped wire, and on this wire you have another wire of length L. Okay, this blue color wire of length L. This blue color wire of length L can slide on this U-shaped wire. Okay, so this can slide on the U-shaped wire. Okay, acha. Now there is a magnetic field here. It is a transverse magnetic field. So it is perpendicular to the plane of the paper. For you it is paper, for me it is mobile. I am drawing this on mobile. So it is perpendicular to the plane of the screen and it is directed inwards. Okay, now let's say B is the strength of the magnetic field. Okay, acha. Now suppose this is moving in this direction with velocity v. Okay, with velocity v. So this wire slides to this position. This position from here, moving through a distance dx in time dt. Okay, acha. Now see, initially when the wire was at this particular position, it was enclosing this area. Okay, and now when it has moved to the new position, this particular position, now it is enclosing this area. Correct? So that means, what is the change in area? This is the change in area. Correct? So how much area has changed? dA, it will be equal to area of this portion. Okay, what will be the area of this portion? L is the length and this distance is dx. So it is L dx. Okay, acha. Now see, because of this change in area, there is a change in flux. Okay, so what is the change in flux? d phi, it is equal to B dA. This is the change in flux. Okay, where dA is this quantity. So this is equal to BL dx, isn't it? Acha. So now what will be the induced EMF? Induced EMF is d phi by dt. Okay, so that is equal to BL dx by dt. Okay, now it has moved through a distance dx in time dt and it is moving with velocity v. So that means dx by dt, this can be replaced by v. So that gives EMF, it is equal to B BLV. Okay, so this is the expression for EMF induced across the two ends of this conductor, which is moving in a magnetic field, and this is called motional EMF. Motional EMF. Motional EMF. Okay, so this is one way of deriving the expression for motional EMF, and EMF is equal to BLV. B is the strength of the field, L is the length of this conductor which is moving in the magnetic field, and V is the velocity of motion of the conductor. Okay, now let us analyze this situation in another way. So this is method 2. We have seen method 1. Now method 2. See, if you observe the conductor in the previous case, suppose this is the conductor. Okay, and it was moving in a transverse magnetic field. So what was the direction of the magnetic field? Magnetic field was perpendicular to the plane and directed inwards. Okay, so this is the magnetic field, and this conductor which was moving in this direction to the left, okay, with velocity v. Okay, acha. Now this conductor has electrons. Okay, now these, see, this conductor, it is moving in this direction. So that means these electrons are also moving in this direction, means along with the conductor, and there is a magnetic field. So charged particle moving in the magnetic field will experience a force, and this force is called Lorentz force, isn't it? Now Lorentz force, it is given by the expression F is equal to Q V cross B. V cross B. Okay. Acha. Now here we have electrons, so we have force on electron. It is equal to minus E V cross B. Okay, so that means force will be in the direction of negative of, this is minus sign, negative of V cross B. Okay, now see here V is towards left, and magnetic field, it is directed inwards, so this is magnetic field. Okay, now V cross B, if we take V cross B, it will be in the downward direction. Okay, but negative of V cross B means the force will be in the upward direction. So that means the electrons, these electrons, they will experience a force in the upward direction. Okay, so force on the electron, it will be in the upward direction. Okay, acha. Now what is the work done? Work done by the force, this force. This electron will move through length L of the conductor. Okay, so work done will be EVB. This is the force. Okay, see V and B, they are perpendicular, so I am writing VB. EVB. Okay, here I am taking this work done on the electron. Okay, here force was in vector form, so I have written the sign of the electron, taken the sign of the electron. Okay, work done is equal to EVB. Here I am taking the magnitude EVB times L. Okay, EVB times L. Okay, this is the work done. Okay, now what is EMF? EMF is work done per unit charge, because EMF is potential difference. Potential difference is work done per unit charge, isn't it? So work done per unit charge, this quantity W divided by E. So this is equal to how much? B L V. So we have EMF is equal to BL V. Okay, so this is another way of deriving the expression for motional EMF. Okay, now there is one more approach to the same concept. Okay, now let us check the third approach. So now the third approach is, see, this is the conductor. Okay, now electron is moving in the upward direction. Okay, now since the electron is moving in the upward direction, so upper end will acquire a negative potential and the lower end will acquire a positive potential. Okay, acha. Now see, the Lorentz force is causing the electron to move in the upward direction. Okay, now here we have negative charge and here you have positive charge. So because of that, there will be an attractive force. Okay, so this attractive force will cause to acquire an equilibrium state. Because see, Lorentz force, it is separating the charges. Okay, here you are getting negative charge buildup and here you are getting positive charge buildup. But so that is due to magnetic force. Okay, but electrostatic force will come into play, which will cause an attractive force between the two opposite ends. Okay, so what happens at equilibrium? What happens? This electrostatic attractive force balances the repulsive force that is produced due to, not repulsive exactly, actually this charge buildup, because electrons, they are moving in the upward direction. Okay, but at equilibrium state, this process will stop. Okay, so Fe will be equal to Fb. Now Fe is equal to force on electron due to electric field. Fe is equal to Ee, charge of electron times the electric field, and magnetic Lorentz force, it is EVB. Okay, so that gives E is equal to V times B. Okay, this is electric field. Now we know that electric field, it is equal to potential divided by length. Okay, now here potential means EMF, so EMF divided by length. Okay, so this is EMF divided by length is equal to VB. Okay, or EMF, it is equal to BLV. So this is another way of deriving the expression for motional EMF. Acha, now regarding the direction of flow of current. See, when this conductor is of length L. Okay, this conductor of length L. Now it is moving in this direction with velocity V. Okay, and here you have the magnetic field. Okay, it is directed inwards, given by B. B is the magnetic field. Okay, acha, obviously when this conductor moves in this direction, so the area of this part, it is going to decrease. Okay, suppose now the conductor is at this particular point, at some time later it will move to this point. So now for the flux, this will be the area considered. Okay, so that means the flux enclosed, it is decreasing. Okay, flux enclosed, it is decreasing. So now Lenz law, it says that the direction of induced EMF is such that it opposes the change in magnetic flux. So since the magnetic flux is decreasing, the current should flow in such a direction so that it should oppose the decrease. Now how to oppose the decrease? That means the induced EMF will be such that it will produce a magnetic field in this region, which will be in the inward direction. Okay, so it is marked by these blue crosses. Okay, where these blue cross represents B induced, and it is in the inward direction. Why inward direction? Because flux in the inward direction is decreasing, because area is decreasing. So to compensate it, this induced magnetic field will be in the inward direction. Okay, so to have this induced magnetic field in the inward direction, what should be the direction of current? By Fleming right hand rule, we can say that current should flow in the downward direction. Okay, so that means when this conductor moves towards left, the current in the conductor will be in the downward direction. Okay, current in the conductor will be in the downward direction. Suppose you have a circular region with magnetic field perpendicular to the plane of the paper. Okay, and then you have a rod. Okay, now this rod, it is hinged at this end. It is hinged here, and it is rotating with angular velocity omega. Okay, and let's say L is the length of the rod. Okay, now let's say take one small element of length dx. Okay, now for this small element dx, the motional EMF for dx, length dx, it will be dE. It is equal to, suppose B is the strength of the field, so B times dx into V. Okay, that element is moving with velocity V. Now here different elements are moving with different velocities, but with a common angular velocity omega. Okay, now suppose this small element, it is at a distance x. It is at a distance x from the axis of rotation. Okay, such that V, it is equal to omega x. Okay, so this gives dE, it is equal to V is omega x dx. So this is the EMF induced for that small element. So total EMF induced will be obtained by integrating this. So it is 0 to E and x. So this element can exist from this end to this end at any location. So it is from 0 to L, where L is the length of the conductor. Okay, so if you integrate this quantity, it is equal to L square by 2. So L square by 2 multiplied by this is EMF. So EMF is equal to B omega L square divided by 2. So this will be the EMF induced between the two ends of this conductor, rotating in a transverse magnetic field with angular velocity omega. Okay, so this is one, you can say it problem. This is actually given in your NCRT. This question is given in your NCRT. It is a solved example.